All right. Okay. So today we will cover chapter 8 in the textbook. Okay. And chapter 8 is all about paired data, comparison of paired samples. Okay. And so we're going to see things that are similar to what we saw in chapter 7, but in particular, we are going to cover the paired t-test. And then we'll look at the confidence interval for a, I guess, a mean difference. Then we'll look at the sign test, which is non-parametric. And we'll also look at the signed rank test. Which is also non-parametric. Excuse me a second, let me just check. Okay. Okay, so somebody just joined. No, there. I have not posted the slides, and so everything's going to be handwritten today. So just sorry for the change up here. Okay. Yes. All right. And so this all applies for kind of paired data situations. Okay. So when you look at a paired data, basically at first glance, it might appear that you have two samples, okay? But the key difference here is that every observation in one sample is paired to an observation in the other sample, okay? All right, and so in some cases, we could even think of it as just having one sample where you have kind of two measurements, okay? Having one sample, but each observation consists of two measurements. Now, this is not always the case. Sorry, the all right, give me a second here. Everything's fine. Mom, not my mom. my kid's mom, my wife, is taking the kids out for to get food and play at the park, but that meant stopping the art project that she was working on. So, you know, yes, and I did say I was going to post these handwritten notes to CCLE after lecture. So, anyway, let me go ahead and yes, I will save all of these things. This is week 4, Tuesday, and this will be okay. All right, so let me just we'll take a look at a few examples, but maybe some scenarios. Okay, you can have kind of before and after situations. You can have basically like twin studies, which I would say is fairly rare, but not rare, but it's hard to pull off. But a lot of times you'll have matched cases. Okay, so let me just pull up an example from this from the textbook here. Okay. Okay, so here we can look at this is from the 4th edition of the textbook, but here we are looking at you know, this example says, does drinking coffee affect blood flow, particularly during exercise, right? So sometimes you drink coffee and, you know, there's caffeine and it stimulates, you know, different parts of the body and things like that. And so, you know, they measured myocardial blood flow during bicycle exercise before and after giving the subjects a dose of caffeine that was equivalent to drinking 2 cups of coffee, okay? And then we're looking at the myocardial blood flow MBF levels before and after the subjects took a 200 milligram tablet of caffeine, okay? And so if we look at the data, this is what our data look like. And I'll go ahead and let me just copy this into our plot here. So here is, this is what it looks like. And there's also kind of a corresponding plot. But, you know, let's just, let's look at this. And, you know, what if I ask, you know, is there a difference, right? Does caffeine make a difference, or basically is there a difference between baseline and caffeine? Okay, and so let me first show you what would happen if we do it the wrong way. Okay, this is the wrong way. I don't know why the R is capital. Okay. The wrong way would be to treat this as just a t-test for independent groups. Okay. So again, this is the wrong way. Don't do it this way. The null hypothesis we would do is mu1 versus mu2. Okay, so where, you know, group 1 is baseline. Group 2 would be caffeine. All right, and let's just start off with the alternative, not equal. Okay, not equal sign. Okay, two-sided alternative. All right. Okay, so we'll calculate our standard error. We have 8 observations. So we would do 0.83 squared over 8, 0.86 squared over 8, and we'll get some measurement here. We get 0.4226, okay? And our test statistic would be y bar 1 minus y bar 2 over our standard error. So we might get a significant value here, but let's just check it out. Okay, so I'm going to do 5.4 minus 3.99 divided by our last answer. I get 2.721. And then I'll go to my reference tables. We're going to we would say we have, if we assume degrees of freedom, is n1 plus n2 minus 2. 14 degrees of freedom. We would look up 2.721, 14 degrees of freedom, and we get a value between 0.01 and 0.005. Okay. I'm sorry, tail area. .01 and 0.005. And then, and if we double it, okay, so our p-value is doubled because of the not equal sign. In the alternative. And so our p-value is between 0.02 and 0.01, okay? And so with, let's say, alpha equal to 0.05, we would reject the null hypothesis. But if somebody wanted to be more cautious and use alpha equal to 0.01, we would not reject the null hypothesis. Okay. Is that all right? Does the work I did here feel okay regarding kind of doing a t-test? All right. But again, this is the wrong way. All right. So what is wrong about this approach? Okay. This approach is wrong because we're treating the two groups as being completely independent from each other. Independent from each other. And the the truth is that if subject 1 had a high value at baseline, they're more likely to have a high value when, after they took the drugs or whatever. And if another subject had a very low value at baseline, they're more likely to have a lower value after the fact, right? And we can kind of see this when we look at the corresponding chart here, right? Now, not the caffeine doesn't affect everybody in exactly the same way, right? So some lines, the change is steeper, right? So here was subject 1, and the drop was fairly dramatic, and here's some of the other subjects, and their drops perhaps not as dramatic, okay? But just looking at the chart, we look at what was myocardial base flow at baseline, and what was myocardial base blood flow after taking a caffeine. Every single one, all 8 out of 8, everyone experienced a drop in myocardial blood flow if you look at the chart, okay? And so what we need to do is we need to treat the before and the after as being joined together. That these are not just 8 random people, and these are not 8 separate random people, but these are the same 8 people. And what we're seeing is kind of across the board is that, people in general who start at higher will end up kind of higher over here, and people who are on the lower end will end up kind of on the lower end over here. And so if we take the, so we got a significant value, and we would still reject the null hypothesis at the 5% level, but if we want to be more cautious, we might say, oh, we wouldn't reject at the 1% level. But that's the wrong approach, okay? The correct approach would be to treat the data as being connected, all right? And so let me once again copy, whoops. So copy here. Let me take this data, we'll put this here. And let me actually get this chart here. So looking at this, okay, every single person experienced a reduction of myocardial blood flow, okay? And so the correct way approach the data is we treat the observations as being paired. Okay, and so what this means is that we have to calculate a column called the difference, and we're going to call this D, all right? And so we're going to go through and we're going to, for each of these values, I'm going to subtract off 6.37 minus 4.52. You know what? Let me change my setup that I want. Oh, okay. And line output. All right. 1.85. All right, so I'm going to go through and I'm going to calculate all these differences. 5.69 minus 5.44. So we get a difference. So this is basically reduction. Okay, so these are our values. I'm going to have to calculate the mean of these values. So let me mean and standard deviation. This is a little bit less fun here, but let's go ahead and do this. All right, so we'll just these values 1.85, 0.25, 0.88, 1.6, 1.05, 1.67, 0.22. Okay. So we can ask for the mean of x, and we get 1.15375. And then we can ask for the standard deviation of x, 0.629. Okay. So we're going to ask, are these differences significant here? So this is the mean and the standard. So we treat the observations as being paired. Can we read the equation we're supposed to use for the standard deviation? So the standard deviation is the square root of the sum of y minus y bar squared over n minus 1. So you take the difference between each value and the mean, you square those differences, add them up, divide by n minus 1, and you take the square root. Okay. You can always you can use R. I know from one of the quizzes I had you calculate R standard deviation by hand, but the reality is no one really does that. Okay, you can use your calculator, you can use R to help you. All right. So we're going to treat these observations as being paired, and what that means is we calculate a column of differences. Okay, and then once we calculate this column, we can basically ignore the two original columns. Okay, so here we're going to define the difference. D is going to be equal to baseline minus caffeine. Okay, and now our hypotheses, and this is kind of the hypothesis is different. The null hypothesis is that the mean difference is equal to 0. Okay, so note there's only one parameter in the hypothesis. And that's the mean difference. In the hypothesis, okay? It is wrong to use mu1 minus mu2, okay? Because this implies that there's two different means and you're asking for the difference between the means. Here we're asking for, is the mean difference, is the mean of this column, the difference, equal to 0? And the alternative, we'll keep it being non-directional. We'll ask, is it not 0? All right. Okay, and so our standard error, so this is really the only column that matters. So we're going to just kind of ignore those things. The standard error is going to be the standard deviation of the difference column divided by the square root of n of the difference column. So in our case, we're going to do 0.629 divided by the square root of 8. Okay, so let's go ahead and do that. 0.629 divided by square root of 8. All right, so I get 0.222. 0.222, we'll just do 0.2224. Okay. All right, and so now the test statistic T is basically the mean difference divided by the standard error. Okay, and we're basically asking, is it different from 0? So I've got 1.15375 over 0.2224. Let's go ahead and, oops. Check this out, 1.15375 divided by the answer here. And I get 5.188. So we compare this versus the kind of, in our previous answer, I think we had, we looked at 14 degrees of freedom and our number was like something like 2.7 or something. This time, okay, our test statistic is like much farther away from 0, right? It's like at 5. Okay, so it's going to be very, very significant. So we're going to look this up. What do you think our degrees of freedom will be? How many degrees of freedom do you think I have? Yeah, because we're only treating it as having one column of values, it's going to be n minus 1. So we're going to have seven degrees of freedom. Okay, so that's the key. We only have, we're going to ignore kind of these two original columns, and we're going to just treat it as if we only have one column of values. So we only have 7 degrees of freedom. So I'm going to go to 7 degrees of freedom. I'm going to look up this test statistic, in our case, 5.188. All right. And so now my tail area is between 0.005 and 0.0005. Okay. Okay. And so my p-value would double. Okay, between 1% and 1/10 of 1%. So very small. And so this would, we would reject at, what's going on here? Reject at alpha equal to 5%, reject at alpha equal to 1%. Okay. And we would say we have evidence that there is a difference, that the difference between baseline and caffeine is not 0. Okay, we have evidence that I need to figure out where to write this. Sorry. So it's not a difference between means, but it's a mean, that the mean difference. So we have evidence that the mean difference, okay, there's only one difference now, that the mean difference mu d between baseline and caffeine is not 0. And in this case is greater than 0. Okay, in our case. I think this is something that perhaps confuses some students, is that your alternative hypothesis, okay, you can start off with your alternative hypothesis as being non-directional, right? Which just means we're looking, is it different? And then you go through the process and you look at your data. And if the data says, hey, the difference is greater than 0 and it's significant, you are allowed to make that conclusion and say, yeah, there is a difference and that difference is positive. Or yes, there is a difference, it's not 0 and that difference is negative. Okay, it's okay that your alternative hypothesis started off non-directional and your conclusion ends up being directional if the data supports that, right? Your data supports that you're supposed to reject the null hypothesis, accept the alternative, and you don't have to just say, oh, the alternative said there's a difference and we don't know if it's bigger or smaller, okay? Prior to looking at the data, you didn't know if it was going to be bigger or smaller. After you look at the data, you can just say, yeah, it was bigger than 0. And that's fine, okay? So before looking at the data, you can say, I'm not sure. So we're going to just check to see if there's a positive difference or negative difference. But then after you look at the data, if there's a positive difference and that difference is significant, you might as well just conclude that, yeah, it's a positive difference. Okay. All right, how do we feel about this? And do we feel comfortable about the difference between treating it as independent and treating it as paired? Okay, so the key is that we have to treat this as paired data, right? When we have this kind of, when you have the same kind of subjects and things like that. So going, hand in hand with this is we can have the confidence interval. All right. All right. Okay. So the confidence interval for the mean difference. Okay. And that's basically, all right, so we'll just do step 0. Well, step 1 is, find the difference column. And then find the mean difference and the standard deviation. All right, and then the step 2 would just then be use the formula. And the formula is pretty much the exact same thing as a confidence interval for one sample. Okay. It's just that in the center, you're going to put in the mean difference plus or minus the value t, okay, times the standard error, which is s over the square root of n, okay, but for the difference, okay. All right, and so where did these numbers go? Okay, so these are the values. So we have 1.154, we'll just say. All right, so we have d bar, previous slide, 1.154. The standard deviation of these differences, 0.629. And the number of observations is 8, okay? So if we want to make a 95% confidence interval, it's going to look, the mean difference, we're going to have 1.154 plus or minus, we're going to do 95% confidence, 7 degrees of freedom. So this is the column for 95% confidence, 7 degrees of freedom. We have 2.365. 2.365 times the standard deviation, 0.629 over the square root of 8. So I have 1.154 plus or minus, and what does this number come out to be? Okay, so we're going to do 2.365 times 0.9 divided by square root of 8, 0.526. Okay, so 1.154 minus 0.26, 0.628. 1.68. Okay, all right, and so our 95% confidence interval is this, and we would say I am 95% confident that the kind of mean, I guess, change from baseline to caffeinated or to, I guess, after caffeine. I don't know how to I guess the mean change, I would say, in myocardial blood flow. I just say blood flow from baseline to caffeine is between 0.628 to 1.68. Okay. All right. So this is correct. Now these are subtle subtle differences. Okay. Don't, I will say, do not say I'm 95% confident that the difference. So we're here, there's only one mean, okay? Only one. And it would be incorrect to refer to having two means. So if we would say that the difference between, you know, mean baseline and mean caffeine, mean after caffeine, is between blank and blank, and 1.68 and 0.628. All right, and these like look the same, but it's correct, right? Is, you know, talk about only one mean existing. And then wrong is to kind of talk about the existence of two means. Two separate means. Okay, because two separate means kind of implies that there's two populations, but there's only one population, and we're just looking at the difference that exists in these populations. There's a question, it says, how do we find the value for T star? Sorry, I must have missed that question earlier. So the T star here, T star comes from the table. With the number of observations minus 1 degrees of freedom, with your degrees of freedom equal to n minus 1 df, and in the column for the chosen confidence level. Okay. And so I recognize that these sentences, you know, they sound very similar. And, you know, when someone's talking, it's almost, you have to really be paying attention to kind of hear the difference. But here we're talking about kind of just the mean change. And here we're talking about the difference between means, okay? And so if you hear difference between means, that's wrong. That's having two separate means. And here we're just talking about kind of the mean difference. There's one mean, and it's for the difference. All right. Is that okay? Questions about any of this stuff? You know, I've totally forgotten about your view quiz answers. So your first view quiz answer, today's first view quiz answer is E. E as in elephant. E as in elephant is your first view quiz answer. All right. Okay, let's, you know, our lecture today will be a little bit probably on the shorter side, but well, I don't want to make any promises I can't keep. But let's take a look at the sign test.
Here's something I found on the web. According to Coursera.org,
Okay, so
the sign test can be used to test whether a sample quantile differs from a hypothetical population quantile.
apparently, these listening spy devices in my house, which make my life convenient, also thought I was talking to her. So, well, I wasn't. Sorry, but thank you for that bit of information. Okay, so the sign test is a non-parametric test, and yes. So, what is a non-parametric test? Okay. Okay, so non-parametric test means just we do not place distributional assumptions, on the kind of the sampling distribution. So when you do the t-test, when we do the t-test, we're assuming that the central limit theorem works, okay? And, we didn't get into like the theory of the central limit theorem and stuff like that. If you were to like major in statistics, if you were to take a mathematical statistics course, say Stats 100B or, Math 170S or something like that, you would prove the central limit theorem or at least derive it. But the kind of the idea of the central limit theorem is that the sampling distribution of the mean ends up following a normal distribution. I totally forgot, and it's a tiny bit out of place, but it's too cool not to share. So let me pull out my statistics toy. Okay. I don't know. Have you guys seen something like this? Can you guys see this? Okay. So this is an illustration of the central limit theorem, I think. Okay. Well, I hope you guys can see. Let's see. How do I hope you guys can see this. All right. So what we have here at the top, okay, there's all these tiny little beads down here. Okay. And I'm going to flip this over and they're all going to kind of go into this little funnel at the top. And then I flip it over and then they scatter down like sand and then they fill out this thing and it ends up looking like the normal distribution. So how does that work? Okay. Well, this is actually kind of an illustration of both the central limit theorem and also kind of the normal approximation to the binomial. Because what you can think is, so the little beads, they fall down and they hit each of these these little pegs, okay? And then when they hit the pegs, they basically, you can kind of just simplify and say, they got a 50% chance of falling to the right and a 50% chance of falling to the left. And so some fall to the right, some fall to the left, and then they hit another line of pegs. And then again, they have a 50% chance of falling to the right, 50% chance of falling to the left, so on and so forth. And so every time it hits a different row of pegs, it can either, fall more to the right or to the left or somewhere in between. And so can some of the beads end up all the way at this far side? And yeah, it can, but it would have to go, I don't know which way it is for you, but it would have to go right, 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 right. And it would have to hit right a whole bunch of times in order to end up all the way over here. Okay, likewise, to end up over on this side, it would have to go left, 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 left. Okay. And so there's only, like one, it's got to get kind of hit all of those lefts in order to get all the way over here. Whereas to end up in the middle, there's a lot of different paths, right? Right, 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 left, 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 right, 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 left, right, left, right, left, right, 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 left, left. There's a whole bunch of different ways to end up getting into the middle. Okay. And so you can think of each of these things as either going right or going left as kind of this binomial experience. And whether they end up all the way over here or end up all the way over here is going to be kind of the sum of that. And similarly, to kind of go along with the central limit theorem is if you just think of these, rather than going right or left, you just think of them as zeros and ones and kind of, what's the mean? Because basically the mean is just you take the sums of zeros and ones that are whatever numbers you have and you take the average. You're also going to end up getting something that looks kind of like this here. All right, and so we can flip this over, and I'm going to flip it back. And what do we see? All right, can you guys see that? All right. I'm just watching my own video here. So, so I hope this is kind of cool. And then I thought it was cool. All right, and so you get when all the beads fall, they end up following the normal distribution. Of course, it's not perfect. Over here we got some bins ended up too high and some bins ended up too low. But overall, when you do this again and again, you get something that follows the normal distribution very, very closely each time. Okay, well. Well, I thought it was neat. All right, so what are we doing? Oh, okay, so we're talking about non-parametric tests, and the the whole idea here is that that system assumes things follow the normal distribution. It follows a parametric distribution. Okay, now sometimes you're in a situation where you can't assume that things are going to follow a parametric distribution like the normal distribution. And, you have like these, really big outliers or something like that. And so for a non-parametric test, we don't place any kind of distributional assumptions. Okay. And so the sign test is, there's no it's non-parametric, but it's fairly weak. Okay. But weak, right? And what does it mean to be weak? Okay. Weak means lacks power. And do we remember what it means to lack power? So as far as a test goes, when we say it lacks power, this means it will not reject the null hypothesis in many cases where it should. It basically commits type 2 error frequently, okay? Will not reject the null hypothesis when it should. Okay, this is prone to type 2 error and requires very strong evidence to reject the null. Okay, but it's you don't place any kind of parametric assumptions, and effectively, if you want to be kind of very cautious, right? Use when you want to be cautious in your conclusion before you reject, right? So use if you want to be cautious before rejecting the null. All right, and so the sign test is pretty simple. Okay, let's just go back to this type of if we take this data here, okay, and we just say, okay, what is the sign of the change? Okay. And so we would say, we have a positive. Okay, so you have, you're going to be positive if y1 is greater than y2, and negative if y1 is less than y2. Okay, so we say, all right, what is the sign? All right, and so all we do here is we're going to say, okay, this is a positive change, right? Baseline, you just have to choose which one's going to be y1 and which one's y2. So baseline is greater than caffeine. Observation 2, baseline is greater than caffeine. Observation 3, baseline is greater than caffeine. Observation 4, baseline is greater than caffeine. Observation 5, baseline is greater than caffeine. So in all of these observations, we have baseline is greater than caffeine. And so this is very simple. When we look at the paired data, we go, oh, you know what? Does caffeine make a difference? And, for all 8 people, there was a positive difference. Okay, and so we would just end up counting all of these things, all right? And you have basically n positive and n negative, okay, which is number of positive differences and n negative would be the number of negative differences. Okay, so in our case, n positive is 8 and n negative is 0. Okay. All right. When you do the sign test, okay, the null hypothesis is basically the values for baseline and caffeine are similar to each other, right? So that that basically, as far as differences go, there's about an equal chance of having a positive or a negative difference. Okay. How do I express this? The distribution of differences between kind of baseline and after caffeine is just as likely to be positive as it is to be negative. Okay, and then the alternative, you can have non-directional. Okay, you can just say it's the differences are not equally likely to be positive and negative. And the directional one, you'd say, more likely to be positive or more likely to be negative. Okay, or Okay, and so you go through, and so in our case, we have 8. And for a non-directional one, you use the larger one. Okay, so for non-directional, the test statistic is the larger of n positive and n negative. Okay, so we're gonna use 8. Okay, and then at this point, we will go to a reference table. Where is it? So we have critical values for the sign test. Okay, and this is pretty much it. So with 8 observations, really for it to be kind of significant, you would need to have 8 positive or 8 negative. So if you have 8 positive, then you would have 0.008, okay, for your corresponding p-value. So with 8 observations, we observed 8 pluses. And so the and there's kind of, I know there's also a little bit of confusion, like when do I do the pluses and the when do I double it versus divide it in half and things like that. And it just, the answer is it depends on the table. And so as far as our tables go, with table 6 for the Wilcoxon-Mann-Whitney test, it says this table provides values in bold type and the corresponding p-value for non-directional alternative in italics. Directional p-values are found by dividing the number in italics in half. You look at table 7 and it says something very similar. Corresponding p-values for non-directional alternative is in italics. Directional p-values are found by dividing the number in italics in half. And so, so here we go, okay? We have a question that says, is the null hypothesis saying that n plus is equal to n minus? It's saying effectively something like that, where we would expect n plus to be equal to n minus, okay? If the null hypothesis were true, we would expect n plus to equal n minus, but we're not explicitly saying that in the null hypothesis, right? So, because n plus and n minus are the values that you get in your sample. And so we know that those things are subject to randomness, right? So in the null hypothesis, we're saying the population is, looks kind of like this. And so when you draw values from the population, we would expect our positive and our minuses to be about the same, but we're not necessarily saying that n plus will be equal to n minus, okay? Because we're allowing for some random variation, right? So you could have baseline and caffeine, or you could have some other scenario where we're not expecting one to really be bigger or smaller than the other, but because we know there's randomness, sometimes it's going to be positive and sometimes it's going to be negative, and they're not necessarily going to be exactly equal to each other. So so we're saying that we would expect them to be equal, but not necessarily. So we're going to just say the difference between baseline and after caffeine is just as likely to be positive as it is negative, okay? When you say use the larger of n plus and n minus, do you mean use the one which has the highest count? Yeah, so in our case, we have 8 and we have 0, so 8's bigger than 0, so we're going to use 8. And it would differ from one sample to another. Let me see if I can do that. Okay. All right, and so we would go to the table, and our corresponding directional p-value for the number of signs or number of differences we have is 8, and our test statistic is 8. So our corresponding p-value for a non-directional alternative, which is what we have, our corresponding p-value is 0.008. So we go to the sign table. And the non-directional p-value. .008. Oh dear, something happened. What happened here? Stop. Okay. All right. Okay. Well, I don't know. Geez. It's close enough. All right. How do we feel about the sign test? So again, so our test statistic. How do we find the test statistic? Here, you know what? Let's do another example. Okay, so we just so I don't leave you on where are we? Okay, paired. Okay, let's go to the sign test. Let's find another example. How do I use this? All right, let me just read this example from the textbook here. Okay, so here, oh geez, what a morbid example. All right, it says skin from cadavers can be used to provide temporary skin grafts for severely burned patients. The longer such a graft survives before its inevitable rejection by the immune system, the more the patient will benefit. A medical team investigated the use of matching graft to patient with respect to HLA, human leukocyte antigen system. Okay, each patient received 2 grafts, one with close compatibility and the other with poor compatibility. And then we measured survival time. Okay, so so this, this is, if you think about the logistics of conducting such an experiment, this was, I'm sure this was not an easy experiment to pull off. But we had 11 patients, and both of these had different things. And the part of the reason why we would want to run such like a non-parametric test in a case like this is because in some of the cases the value is long or incomplete, right? And so it says that a t-test cannot be applied here because 2 of the observations were incomplete. Okay, patient 3 had died with a graft still surviving, so we didn't actually get the true value here. Okay, so in some cases it got rejected and we recorded the number 93, but here the number is 57, which is kind of the time that we had measured. But unfortunately this patient had died, so we didn't actually get the real number. It was just kind of like, well, it was going to be more than this. Okay, and similarly, something happened with patient 10. We don't know unspecified reason, but we don't actually have the actual measurement. We just know whatever it was longer than 60. Okay, and so we can't conduct a t-test because we don't actually, the true value is not known. Okay, but we do know we can compare these and say, plus or minus or something like this. Okay, we have a question. It says, will we ever be given a situation where we have to determine if it's better to use a paired t-test or a sign test? So looking ahead to the final exam, I'm going to have a section where I will kind of describe a scenario, and I'll ask you, what's the appropriate test to use here? I think in that scenario where I ask you, what's the appropriate test, I will try to keep it fairly straightforward, where it will be fairly clear that in this scenario, you can't be using this kind of test or something like that. So it'll be probably a little bit more clear where it'll just be like, should you use a paired t-test or a just regular t-test or something like that, right? figuring out whether you should use a sign test and later on the signed rank test and things like that, it gets a little bit more complex and maybe sometimes a little bit more subject to I don't know, just different things. So I'll try to keep those questions straightforward. And there will be a section where it'll just be like, here's the scenario, what's the appropriate test to use? And then when it comes to actually like performing a test where you have to figure out an answer, I will say, here's your data, here's the scenario, and perform this particular test. Okay. So anyway, this would be a scenario where the sign test would be appropriate because using a t-test, we don't actually have the numbers themselves. Now, somebody could just say, well, let's just use 57. Let's just use the number 60, but that's perhaps not the most accurate way to do it. But anyway, we go through and we just say, okay, is y1 bigger than y2 or not? And so we have positive values, and then we have a negative value. Okay, so we have out of our 11 patients, we have 9 that are pluses and 2 that are minuses. Okay, so we go through and we do 9 that are pluses, 2 that are minuses. And so in this scenario, our test statistic is going to be the larger. Well, in our case, we're going to use 9, okay? Because the alternative predicts in this scenario, when we read the problem, it said we want to see if the survival times and here, let's carry out a sign test to compare the survival times, and we're going to use a directional alternative, which is that skin grafts tend to last longer when the compatibility is close. Okay, so we're going to do we want to know if the skin grafts do end up lasting longer if the compatibility is close. So in this case, we have a directional alternative. And in this case, the direction we're expecting is that these values in close are greater than the values for poor. Okay, so we're expecting to see more positive values. So in that scenario, the test statistic we're going to use is going to be the positive value. Okay, now if we had a non-directional alternative, we would have just used the larger between 9 and 2. But in this case, we're going to use the 9 because we said it's positive, and that's also the larger value. And so now we go to our reference table. And in this case, we would do, we have 11 observations and we have 9 positive values, okay? And so our non-directional p-value would be 0.065. And because it's directional p-values are found by dividing the numbers in italics in half. We're going to take this number 0.065 and divide by 2. So our corresponding p-value, well, apparently they got a little bit more accurate by using a computer, but we would have just done 0.065 divided by 2 and we've gotten 0.0325. They got something 0.03272, but that's effectively what we would have gotten if we used the table as well, 0.0325. There. Is that okay as far as the system that we follow for the sign test? Okay, so maybe I'll just copy a couple slides here. This, oh geez. When it says directional, we use the n plus or n minus depending on what the alternative is. You would use the n plus or the n minus. What happened here? Okay, sorry. These this textbook here. Okay. Now this is from the textbook. Okay. And we have n positive equal to 9 and negative equal to 2. Okay. And the null hypothesis is pretty much we expect similar values or n plus and n minus, okay? And then the alternative is basically we expect, these are not really good hypotheses, but here we're basically expecting more n positive. That means close compatibility. It's going to be greater than poor compatibility. Okay, and so because we're expecting more n plus, we use n plus as our test statistic. Okay, so we have our observations 11, our test statistic, which they call BS, is 9. B for the sign test is this, and we're going to look up 11 and 9, and the value for non-directional, the non-directional p-value table is 0.065. Okay, our alternative is directional. Okay, so our p-value is half 0.065. Okay. All right, so that's what we've got. 11.0965.0225. Okay, and then so we have p-value is equal to 0.0325, and if alpha is say 5%, this leads us to reject the null hypothesis, and we say we have evidence. Survival times where compatibility is close. It's greater. Compatibility is poor. All right, so that's the sign test. Okay. All right, and then the last one, oh, here, so let me give you your second view quiz answer for today. Second view quiz answer is C, C as in cat, C as in cat. Okay. Let's do take a look at the signed rank test, and I'm going to just copy the example from the textbook just because the numbers are good. Okay, so again, signed rank test again is a non-parametric test, and this is a little bit more powerful than just the plain old sign test. Okay, so this is the Wilcoxon signed rank test. Okay, so still non-parametric. and a little more powerful than this sign test. Okay, but overall still less powerful than the paired t-test. All right, so here we're going to look at a sample. We've got 9 horses, okay, and a veterinary an anatomist, I don't know how to pronounce that word. Okay, measured the density of nerve cells at specified sites in the intestine. Okay, so I have no idea what this word is or what these even things are, but apparently when you're a horse doctor or something, it just reminds me of like Rick and Morty's mom. But okay, we've got site 1 and site 2, the mid region of the jejunum and the mesenteric region of the, whatever these things are. Okay, we just want to know, okay, what is there a difference in the nerve cell density here? Okay, and these are the measurements here. Okay, and again, this is paired data because we're not taking measurements of 9 horses over here and measurements from 9 different horses. We're basically taking 2 measurements from the same horse. Okay, so anytime you're like looking at the same subject and you're getting 2 measurements, so whether it's before they took caffeine and after they took caffeine, or you know, before something and after, or in this case we're looking at site 1 and site 2, or you know, we had the same patient where you had high compatibility and low compatibility on the HLA skin graft and things like that. Anytime you're taking 2 measurements from the same patient, those are going to be paired data situations. Okay. And so here we have 9 horses. We got a measurement for site 1. We have a measurement for site 2. Okay. And so notice what we've done here, just like we would have done for the t-test, is we calculate a difference column. All right. So all right, so I'm going to do this. We have basically, you know, this is a paired scenario. Two measurements from the same subject, okay? And we basically calculate a column of differences. Let me I want to slide this down. Okay, so we calculate a column of differences. And then what we do is we calculate a column of differences, and then you take the absolute values of the differences, and then you rank them from least to greatest. And so I'm going to go ahead and I'm going to calculate, just copy this over here. Calculate a difference of column. So this is kind of step 1, calculate the column of differences. And then, so you can see this actually ended up copied. And I actually need the whole thing. And then step 2 is take the absolute values. And then step 3 is rank from least to greatest. Okay, so you say, all right, well, you say, all right, which one's the smallest difference? The smallest one here gets ranked 1, right? So this is the smallest. What's the next smallest? 2, the next 2.3, and so on and so forth. And this is basically the greatest difference. Greatest absolute difference. Okay, so this is what we have. Okay. So this is the rank of the absolute values of the differences, and then we go back, and then we're gonna say, all right, which ones were positive differences and which ones were negative differences. So as we go on, we say, you know, what's the rank of the differences, and then we calculate the signed rank. So I'm going to go ahead and I'm going to just copy this part here. So this is not going to fit, is it? Okay, so the greatest absolute difference in the smallest, and then we, how do I fit this in here? All right, well, I'm going to just go ahead and put this right there. We rank them from least to greatest, and then we give them a signed rank. Okay, so you know, that's fine. And we can actually turn the opacity down. Well, I don't know, something. Okay, so we basically, we say, all right, here we had a negative sign, and so this becomes negative. This becomes negative, right? We're looking for the negative signs of our differences. Where did, in which cases were site 1 less than site 2, right? So these are the locations here. So we have -1, -3, and -2. So, you know, coincidentally in our data, the sites where site 1 was actually smaller than site 2, those also are kind of our 3 smallest differences that we've observed. Okay, so we rank from least to greatest, and then we restore signs to the ranks, right? So restore signs from the differences to the ranks. Okay, so we have, so, you know, observations 4, 6, and 8 had negative signs. Negative differences. And then so we make their ranks negative. And corresponding ranks. Okay. All right. And then so now we sum the negative ranks and the positive ranks. Sum the signed ranks. Okay. So for the positive, we have basically 4, 5, 6, 7, 8, 9. You take all of the positive ranks, 4 plus 5 plus 6 plus 7 plus 8 plus 9. And what do you get? You get 39. And then for the negative ranks, you have 1, 2, and 3. So you get a 6. All right, as far as summing the signed ranks. So we've ranked them from least to greatest, okay, using the absolute values. And then we kind of say, all right, which ones corresponded to positive values, which ones correspond to negative values, okay? So it's a little bit kind of like, it's a little bit like the Wilcoxon-Mann-Whitney, but we're basically kind of forming like teams between the, like using the sign test teams, right? Like you have the positive differences and the negative differences. And we're adding up kind of these ranked sums. Okay, and then so now that we have this, we're gonna go to the table, right? So let me go to, let me save this. Let me go to the next slide. So basically our signed rank sums. Okay, we have positive, it's 39, and the negative is equal to 6. And our test statistic will be the larger, use the larger sum. Okay, so the test statistic is the WS. I don't know how they come up with these letters for the test statistics, but there we go. So we got 39, okay? And so how many observations? Our number of observations is 9. And we go to the signed rank table. So there's lots of tables. Can I explain under the rankings? Yes, okay. Okay, so we had a question just going back to how did we do these rankings? Okay. So so if we go, we're okay with, let me just kind of go back to this, right? So if I did this instead of just copying tables, okay? So here are the differences, right? I think we're okay with calculating the differences, right? And then basically we're just going to ignore the signs here, okay? So we're just going to have all the, so we're going to just kind of take the absolute values. So I'm going to just kind of make all of these positive here. So here's going to be the absolute differences. And I say, all right, what's the smallest value, right? So which one's the smallest? So if I'm ranking these, this one's the smallest. And then what's the next smallest? The next. So if I had to put these in order from least to greatest, right, I would go 0.2, 2.0, 2.2. So in order, least to greatest. Okay, 2.2. The next value, it'd be 4.6. The next value after that would be 9.8. The next value would be 10.8, then 12.0, 12.6, and 20.6, I believe, right? So here, the ranks, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to just kind of put those. Okay, so this one is 1, this one is 2, 2.2 is 3, the next value is 4.6, 4, 9.8 is 5, 10.8 is 6, 12.0 is 7, 12.6 is 8, and 20.6 is 9. Is that okay? All right, and then again, we're saying which ones were on kind of the negative team, right? So this was the negative team, this was on the negative team, and this was on the negative team. And that's how I'm getting these, right? So the negative teams, if I add these numbers, I get 6. And if I add the ones on the positive team, I get 39. Does that answer your question? Chat? Okay. So we have, so anyway, we go 9 observations. We go to our table. We're going to go to our reference table, and we got a table for everything, right? So we got critical values for the sign test, and now we have critical values for the signed rank test. Okay. All right. So we had 9 observations, and we're looking for 39. Okay. And we have a number for 37. We have a number for 40. So our number is going to be between 0.098 and 0.039. Okay. 0.098 and 0.039. All right, so our p-value, our non-directional p-value from the table is between, I already forgot, 0.098 and 0.039. Okay, so we use table 8. Look up 39 in the row for ND equal to 9. Okay, so this is how we get that. All right, so how do we tell if this test is directional or non-directional? So it all comes down to what was phrased in the question, and so I keep doing this thing. Let's see. Measured this nerve cell density. The null hypothesis is that in the population of all horses, there's no difference between the two sites, and that's it. They don't say anything about are we expecting a greater difference at site 1, like site 1 to be larger than site 2. So it all kind of depends on how this question is phrased. And as I'm reading this, okay, it says the results for site 1 are here and site 2. So prior to doing this, nerve cell density check, I don't know if they had hypothesized whether we would have a positive or a negative difference, right? And so here for the p-value is 0.09 and 0. So there's weak evidence, we would reject if the null hypothesis is 10%. And here they don't say anything about the test, right? If the p-value would be half, if the alternative were non-directional. Now, we didn't kind of specify that. So our null hypothesis would be, we expect similar values at both sites. Okay, non-directional. And again, it wasn't specified on this problem, so we can't really know as far as this problem goes. Okay, a non-directional one would be, we don't expect the two sites to be the same. Okay, we don't expect similar values at the two sites. And you can have a directional one, right? So I'll say correct direction would be we expect site 1 to have larger values than site 2. Okay, and then the wrong direction would be we expect site 2 to have larger values than site 1. Okay. And of course, we're supposed to write our hypotheses before we even look at the data. And so, if you had written this one, we expect site 2 to have larger values than site 1, and then you look at your data, you say, oh, you know what? After doing this, I'm getting up more positive values than negative values, right? If the alternative were the case, we would expect our negative differences to have kind of a larger rank sum, or signed sum of ranks. And we're not getting that. So in that case, we would say we don't have evidence to support this alternative. All right. Do we feel okay about all of this stuff? And again, so the key here is that if you are taking multiple observations or multiple measurements from the same kind of observations, right? The same subjects, the same people, the same, in our case, animals or things like that, then you have to treat this as paired data. In some cases, you can actually have two different people, but maybe they're paired up for other reasons. So you might want to say, you know, is there a difference between this group and this other group? And maybe they've been paired on like demographic information, right? So we said, you know, we found a person of the same gender and same race and same age group, right? And so we, you know, we might try to match people based on these demographic bits of information. And again, the key is that every observation is matched with another observation. And so if you have everything kind of matched or paired up, then you use a paired test there. Okay, we'll call it a day here. You know, I thought we were going to end early, but we ended up kind of taking up almost the whole time. Let me give you your last view quiz answer. Last view quiz answer for today is the letter A. A as in apple. A as in apple is your last view quiz answer. And I'll go ahead and I'll save all of these notes and slides, and I'll put them into a PDF, and I'll put them online for you guys. All right, we'll end there, and we'll have a good night. Okay, so yeah, last view quiz answer is A as in apple.